Okay, my dear students, today you can start the session. So myself is Vijay Shankar, Department of EC, Chevrolet Engineering College. Today we are going to discuss about the topics orthogonality in approximation signal and the mean square error, mean square value. Okay. And in this also the orthogonality, we already discussed about the orthogonality in concept in vectors, orthogonality concept in signals. Now you can see the orthogonality in approximation signal. Approximation signal. It is not exactly, it's approximation signal we are saying. Let us see. So yesterday I completed this up to the orthogonality in signal and orthogonality vector. Orthogonality in vector, the formula is C is equal to F dot X whole divided by the squared magnitude of X, where F and X are the two vectors. And to find out that equation, the C is equal to F dot X whole divided by the squared magnitude of X. And orthogonality in signal, the C is equal to integral T1 to T2 F of T X of T dt and whole divided by the T1 to T2 X square of T dt. Okay, so the two formulas we already discussed about the orthogonality in the vectors and the signals. Coming to the next one, orthogonality in the complex signals or complex conjugate. The same function what we derive the equation for the orthogonality in signal, only the change is we can take any one of the signal, I'm saying once again, any one of the signal is complex conjugate, then it becomes of the orthogonality in complex signals. Orthogonality in complex signals. So how we can see this is here, like f of t and the x of t are said to be orthogonal over an interval of t1 to t2, that is integral t1 to t2 f of t x of t dt is equal to 0. Okay, is equal to 0. The numerator function becomes 0, then it becomes of the orthogonality of the two signals, so the mutually perpendicular to each other, f of t and the x of t. Okay, now in this, if f of t and x of t are complex signals, f of t and x of t are complex signals, then they are orthogonal over an interval t1 to t2 if the change of function is integral t1 to t2 f of t, the one signal, any one of the signal only. I'm taking here the x star of t. So listen carefully, my dear students. F of t and x star I am taking here. The power. In the power I am taking the star, that is nothing but representing of or denoted as complex conjugate of f of t. Complex conjugate of x of t. And or integral t1 to t2, I'm saying any one of the signal is complex, then it is a orthogonality in complex signals. Here I am taking the f star of t. F star now means in that two signals, either in the f of t or the x of t, one time I am taking the x star, it is a complex conjugate of x of t, and another time I am taking the f star of t. So both are the same. So what is the equation we'll get? Orthogonality in the complex signal means C is equal to numerator the integral t1 to t2 f of t x star of t dt whole divided by the integral t1 to t2 squared magnitude squared x square of t dt, the squared magnitude. So it is not the complex here. Whenever if we can take the magnitude, we'll get the under root of x square plus y square. Complex is nothing but x plus I y only, my dear students. Complex, if any signals is there, the x and y. What is a complex signal? X plus I y. What is the magnitude for that? Magnitude is nothing but under root of x square plus y square only. And phase angle is tan inverse y by x. Okay, that is depends. When x plus iy, if it is in the first quadrant, the second quadrant is changes, third quadrant is changes, and the fourth quadrant is also changes. Okay, so forget about that one. It is a separate topic. It is orthogonality in complex function means only how to change the previous orthogonality in signal equation. C is equal to integral t1 to t2 f of t x star of t dt whole divided by integral t1 to t2 x square of t dt, or integral t1 to t2 f star of t x of t dt whole divided by the integral t1 to t2 x square of t dt. You can keep any one of the signal is a complex signal, then it becomes of a complex conjugate and orthogonality in complex signal. Orthogonality in the complex signal. Let you take the one example. You see here the one example is there. Show that the following signals are orthogonal over an interval of 0 to 1. What is the interval given? It is a 0 and 1. That is a t1 and t2. F of t is given is 1. X of t is equal to under root of 3 multiplied with 1 minus 2t. Okay. So the two signals is given. So what is the formula to find out the orthogonality for the given signals? The formula is you have to satisfy the integral t1 to t2 f of t x of t dt is equal to 0. Then the c is equal to 0. Denominator not at all, it is a 0 because it is an energy signal. So I'm taking only the numerator function and equating the 0. Then the given two functions, nothing but the given two signals f of t and x of t both are orthogonal or mutually perpendicular to each other. Mutually perpendicular to each other. So now I'm substituting the f of t as 1, x of t as root 3 into 1 minus 2t dt. And the interval is from 0 to 1. T1 is a 0 and T2 is a 1. So I take the initial value is a 0 and final value is a 1. Okay. Now 1 into this total function is root 3 minus 2 root 3 into t dt. You'll get the two terms after simplifying this function. And we can split the integral also, 0 to 1 root 3 dt minus 0 to 1 integral 2 root 3t dt. Okay. So integral of constant with respect to anything is, we'll get the variable. With respect to t we are applying, so we'll get the t integral 1 dt, nothing but t. So root 3t, the limitations are from 0 to 1 minus 2 root 3 into t. Integral of t is t power n plus 1 by n plus 1. Okay. Integral 1 dt is t. Integral t is t power n plus 1 by n plus 1. What is the t power here? 1. 1 plus 1 is a 2. So 2 t square by 2 will get. And apply the limitations from 0 to 1 for the functions. And now root 3, upper limit is 1, lower limit is a 0. So 1 minus 0 minus 2 root 3. And here upper limit is 1 and the lower limit is a 0. And 1 square by 2. 1 square by 2 means it's a 1 by 2. Now you can simplify the function. Root 3 into 1 is a root 3 minus 2 root 3 by into 1 by 2. 2 to get cancelled, it is also root 3. Root 3 minus root 3 is a 0. What we got? The integral of t1 to t2 x of t f of t or f of t x of t dt becomes a 0 for the given functions or the given signals. F of t is equal to 1, x of t is equal to root 3 of 1 minus 2t. Okay, both the given signals are orthogonal to each other over an interval of 0 to 1. Orthogonal is nothing but mutually perpendicular to each other. Understood, my students? Like that, we can do the any examples given f of t or x of t using this equation. You can satisfy that whether it is a 0, both the signals are orthogonal. Whether it is not the 0, the signals are not orthogonal to each other. Okay. Coming to the orthogonal signal space. The next one is orthogonal signal space is also the same thing. What we learn orthogonal in signals. Orthogonal signal means it having only the two signals are there. If there is a one signal means we can't say whether it is orthogonal or not. Definitely minimum it have the two. Minimum it having the two signals, so then only we can say that the two signals are having orthogonal, mutually perpendicular and having the 90 degrees angle in between the signals. Suppose more than the two signals are there, we can call it as a signal space. Let x1 of t is one signal, x2 of t is another signal, and x3 of t is also there. Three signals, three-dimensional. I taken here it is a x1 of t is in x-axis, x2 of t is in y-axis, and x3 of t is in z-axis. It's a three-dimensional. Three signals are there. Okay. Are mutually perpendicular, which forms a three-dimensional signal space. Okay, orthogonality is nothing but it's a mutually perpendicular only. It's all the three with the 90 degrees for the 90 degrees of x1 and x2, and the 90 degrees in between of x2 and x3, and the 90 degrees between of x3 and x1 also. When comparing of the two signals, the two signals having the angle in between is 90 degrees. All the three are mutually perpendicular to each other. Again, you can see here the orthogonal signal space is nothing but let x1 of t, x2 of t, x3 of t be the orthogonal to each other. That is, three signals are mutually perpendicular, which forms a three-dimensional signal space. Which forms a three-dimensional signal space, which is also called as orthogonal signal space. Orthogonal signal space, which is used to represent any signal lying in the space. See, if we can take another signal also, x4 of t, when comparing of the two signals only, my dear students, again, two signals is a 90 degrees, then we can say it is orthogonal signal space. Here, some note is there. If there are n such mutual orthogonal signals, n number of signals are there, we have the three means a three-dimensional signal space, we call it as, or orthogonal signal space. If having the n number of signals are there, such mutual orthogonal signals are x1, x2, x3, x4, and so on, xn of t, then they form n-dimensional orthogonal signal space. N-dimensional orthogonal signal space, my dear students. If two signals are there, we can call it orthogonal in signals. Whatever we are using the formula, the same formula also we are using here in the orthogonal signal space, but it having more than the two signals. But comparing of two signals, if I am taking the x1 and x2, what is the formula I'll get? C is equal to integral t1 to t2 x1 of t, x2 of t dt by integral of t1 to t2 x12 square. See, any one of the signal, either it is a f or the x, if I am taking here the x1 and x2, so x square. So suffix I am taking the xn square of t. What is the n here? Either 1 or 2. Either 1 or 2. Okay. Otherwise, if I am taking the x2 and x3, x2 and x3 means the integral t1 to t2, x2 of t, x3 of t dt is equal to 0. You can satisfy that equation. Or the integral t1 to t2, x3 of t and x1 of t. Comparing of any of the two in the signal space, in between there is a 90 degrees mutually perpendicular to each other, then we can call it as a orthogonal. If more than the two, we can call it as a orthogonal signal space. If 3 is there, three-dimensional. If n is there, n-dimensional orthogonal signal space. All right. Now coming to the signal approximation using orthogonal functions. Signal approximation using orthogonal functions. Okay, approximating I am taking, not exact, absolutely, approximately. How we can derive this expression, you can see. Consider a set of signals which are mutually orthogonal over an interval t1 to t2. Now only we discuss about the orthogonal signal space having n number of signals. That n number of signals I am considered as a f of t. Okay, so f of t is approximately I am taking approximately. How we got this equation? F of t is approximately only the c function. There is no any error. Actually, according to the right angle triangle, yesterday we discussed right angle triangle. In that right angle triangle, f of t is in hypotenuse, and the adjacent side is c into x of t, and opposite side there is an error signal e of t. That is a perpendicular line. Okay, the two sides are, one side is e of t, nothing but one signal. Another side, in the adjacent side, c into, nothing but c is a capital C, x of t. And in the hypotenuse, f of t. From that function, according to the right angle triangle, hypotenuse is equal to side plus side. F of t is equal to c into x of t plus e of t. Understood, my dear students? F of t is equal to c into x of t plus e of t. So let us assume the e of t is not is a 0, approximately it is a 0. Now that equation is becomes of f of t is approximately equal to that x I am taking as x1, x2, x3 and so on, moving the c xy x of t is in towards the right side direction, c1 x1 of t, c2 x2 of t, c3 x3 of t and so on, cn xn of t. Okay, so these are all, it is an addition sum of, so I'm just changing that f of t is approximately equal to sum of n is equal to, small n is equal to 1 to capital N, cn xn of t. So cn, when I am expanding this summation, we'll get the c1 x1 plus c2 x2 of t plus and so on, cn xn of t. And where is the e of t here? That only I am taking here the approximately. Following, my dear students, don't confuse here. F of t is equal to, actually from the right angle triangle, cx of t plus e of t. Cx of t plus e of t. I'm taking that e of t, the error is very less. So approximately it is a 0. So the f of t changes as approximately equal to. I'm not using that e of t there. Approximately equal to sum of n is equal to 1 to n cn xn of t. Cn is a suffix, my dear students. C small n xn of t. You see in this what I shared in the meeting here, the f of t approximately equal to the sum of n is equal to 1 to n cn xn of t. Now in the above equation, any of the two signals, that is, I'm taking the xm of t and xn of t are orthogonal over an interval of t1 to t2. If I'm assuming the two signals, we already derived the expression. To find the orthogonality of the two signals equation is, we're taking only the numerator. The integral t1 to t2, one signal I am assuming xm of t, another signal I am assuming the xn of t dt is equal to. See, there is a 0 is there. When it is a 0? When both are not equal. When both are not equal, m and n are not equal. If you say both are equal, means if I am taking that, say m is equal to n, means that equation is becomes of x of t into x of t. X of t into x of t whole square. And integral t1 to t2 x of t whole square dt is an energy signal. Energy signal is not at all equal to the 0, my dear students. Not at all equal to 0. So when both are equal, that is energy signal. If both are not equal, it is an orthogonal. Okay. See, this equation t1 to t2 x m of t x n of t dt is equal to, there is a two equations here. One is a 0. When it becomes a 0, if both are not equal, two different signals. These two different signals, then only it is a 0. We can say it is orthogonal or mutually perpendicular. If both are equal here, m and n means x1 and x1 here, x1 square of t. That is nothing but energy signal. What is that energy signal? En. En. Why you can take it as a En? We already said that's a E suffix E is a error signal. E suffix X is a input signal X of t. Y is a Y of t, the output signal. That N I am taking as a variable. N I am taking as a variable. We can take it as a X only. Okay. The integral t1 to t2 xm of t xn of t dt is equal to 0 for m and n are not equal, and is equal to en when m and n are equal. Okay. Now let us take the function integral t1 to t2 when I am taking the both are equal. Both are equal means x n, m is equal to n. Wherever the m is there, I am substituting the n here. Xn of t into xn of t dt, it becomes of integral t1 to t2 to xn square of t dt. So this n I am taking here the e suffix n. Okay, the energy of the signal. Now, if I am taking it is equal to function. Equal to function means there is a error signal also. Previously I wrote it is f of t is approximately equal to. Okay, according to the right angle triangle, f of t is equal to c into x of t plus e of t. What is the e of t? E of t is equal to f of t minus that signal. So I am taking here the e of t is equal to f of t minus the c into x of t. At c into x of t, to derive the expression for the approximate signal, I am taking the sum of n is equal to 1 to n. Sum of n is equal to 1 to n cn xn of t. Cn xn of t. So previously I take that is equal to approximately equal to the f of t only. Suppose this total equation is f of t minus f of t becomes a 0. E of t. Approximately that I am saying. So there is no error is 0 here. Following. So E of t is equal to f of t minus, it is also the f of t signal only, but it is approximate signal. Not equal to the E of t is exactly the 0. There is an error is there, that is a ignored value. Okay. So f of t minus sum of n is equal to 1 to n cn xn of t. Hence the error energy signal, whatever the equation we use to derive the expression for orthogonal in signals, here also you can use the same. E is equal to integral t1 to t2 e square of t dt. E square of t dt. What is the e square now here? F of t minus sum of n is equal to 1 to n cn xn of t whole square. Cn xn of t whole square into dt. Okay. Now again, to get it is a minimum value or minimized. The error energy will be minimized with respect to the c if applying the first derivative with respect to the c. With respect to the c, nothing but cn here. Okay, with respect to the cn and equal to the 0, then we'll get is as a error is minimized, or error will be minimized. Okay, let us see how to simplify this expression. D by dt or the dou is nothing but partial differentiation, my dear students. D is a differentiation. Okay, in the differentiation both are we are getting the same thing only. D by dt or the d by dc or d by dcn, my dear students. So integral t1 to t2 f of t minus sum of n is equal to 1 to n cn xn of t whole square dt is equal to 0. So after expanding this, a minus b whole square, a square minus 2a is f of t, and b is sum of n is equal to 1 to n cn into xn of t dt, plus b square. What is the b square here? Sum of n is equal to 1 to n cn square xn square dt. And you can split the three parts of the integral with an interval of t1 to t2. First integral, you can see it is independent of the Cn. First integral is independent of the Cn. So the first integral becomes a 0. Okay. First integral, nothing but we are applying here, not the integral, it is a derivative, my dear students. First term I am saying, the first term, integral t1 to t2 f square of t dt, the derivative with respect to the c is becomes a 0. Second term, the integral t1 to t2 sum of n is equal to 1 to n, the cn f of t xn of t dt, here there is a cn is there, with respect to the cn, we'll get the 1. Okay, in this third term, d by dc of the integral t1 to t2 sum of n is equal to 1 to n cn square. The remaining all it is a constant. What is the cn square derivative with respect to the c? 2cn. Okay. So after the simplifying, minus 2, the integral t1 to t2 f of t x n, actually if I am taking, here I wrote the I. Why I? The I values are from 1, 2, 3 and so on, n only. Or otherwise you can use the summation. You can directly put it the summation also. I am removing the summation on both sides. Having the second term having the summation is there, and the third term also having the summation. After equating these two, I am removing the summation and keeping the I there, and I is varies from 1, 2, 3 and so on, n values only. Both are the same. If you are using the sum, or otherwise you can change this x, n is becomes of xi. Okay, minus 2 integral t1 to t2 f of t xi of t dt plus 2ci integral t1 to t2 xi square of t dt is equal to 0. So in these equations, after the simplifying, ci is equal to, or cn is equal to small n. N is equal to 1, 2, 3 and so on, n only. Ci is equal to the same equation what we got in the orthogonality in signals, my dear students. Only the change is I, approximately. So when I is equal to 1, that is a C1, X1. If I is equal to 2, C2, X2. Means moving the C from 0 to slowly the C1, C2, C3. Like that. That is approximately equal. Approximately equal means 89.99 also we can consider as a 90 degrees. That is approximation. Not exactly 90 degrees. The f of t and x of t, 89.99 is also considered as a 90 degrees or 89.98. Okay, or 89.97 is also approximately 90 degrees considered as a 0. Like that. But C1 is minute change from 90 degrees. Ci is equal to integral t1 to t2 f of t x I of t dt under root of integral t1 to t2 xi square of t dt, where I is equal to 1, 2, 3 and so on n values. Okay, this is the equation how to derive for the orthogonality of approximation signals. Approximation signal, approximately. Not exactly, we can say the C is equal to integral t1 to t2 f of t x of t only. But approximation means Ci is equal to, or Cn is equal to. In some of the textbooks, they represented as a, instead of Ci, it is a Cn. Okay, don't confuse. That is a variable only. I is equal to 1 to so on n. N is equal to, small n is equal to 1 to 3 and so on, capital N. N number of signals are there. Following. So we got 3 equations for orthogonality. One is orthogonal is vector f dot c is equal to f dot x whole divided by squared magnitude of x. And orthogonality in signal, the equation is c is equal to integral t1 to t2 f of t x of t dt whole divided by integral t1 to t2 x square of t dt. That is orthogonality in signal equation. If any example is given to find out the orthogonality of between the two functions, given f of t and x of t, we can take only the numerator. We can take only the numerator and prove that it is a 0. The given two functions are orthogonal. It is not equal to 0. The given two signals are not orthogonal. Following. And orthogonality in complex signals means any one, f of t or x of t, can keep it as a star, complex conjugate, f star of t or x star of t. Okay. And now the approximation in orthogonality, approximation signal in orthogonality. What is the equation we derive? Ci is equal to integral t1 to t2 f of t x I of t dt whole divided by integral t1 to t2 x I square of t dt, x I square of t dt. Okay. Next, you go for the another topic, mean square. In yesterday class, in the orthogonality signal, we got the mean square error, mean square error. See, in this equation, in this page, I wrote the Ci is equal to 1 by Ei. Don't confuse, my dear students. Ei is nothing but energy signal only. The denominator, integral t1 to t2 xi square of t dt is equal to Ei I am taking. Okay. 1 by Ei, the integral t1 to t2 f of t x I of t dt is a final equation for the approximation signal. Okay. Approximation signal for the orthogonality. Now, the mean square error. It is a very, very important, my dear students. It is an orthogonality concept for vector, signal, complex functions, ortho, signal space, and approximation signal, and the mean square error. Okay. The examination point of view also, it is a very important. Now you can see how we can derive this expression of the mean square error. We already know error energy signal E is equal to, from the previous slide, integral t1 to t2 f of t minus sum of n is equal to 1 to n cn xn of t whole square dt. Okay. Now you can expanding that function as of a minus b whole square, a square, minus 2ab plus b square. So first term you can see with the integral t1 to t2 f square of t dt minus 2 into integral t1 to t2 sum of n is equal to 1 to n cn f of t xn of t dt plus integral t1 to t2 sum of n is equal to 1 to n cn square xn square of t dt. After expanding the a minus b whole square and take the three terms with the individual integral, we got this expression. Okay. The integration and summation order, if we interchange, see here, the EE, error energy signal, is equal to integral t1 to t2 f square of t dt minus 2 into sum of n is equal to 1 to n cn integral t1 to t2 f of t xn of t dt. So simply you are rewriting this expression, above the expression, plus sum of n is equal to 1 to n cn square integral t1 to t2 xn square of t dt. Okay. And in the next equation, E is equal to integral t1 to t2 f square of t, as usual, the first term. And I'm modifying the second term here. You see the second term I modified, minus 2 into sum of n is equal to 1 to n cn. See, this is a function, cn is multiplied with it, integral t1 to t2 f of t xn of t dt. This is an equation we got from the approximation signal. See, since integral t1 to t2 f of t xn of t dt is equal to cn into en. So you cross multiply these two functions. So in this side, the top Ci is equal to 1 by Ei. If I represent the Cn, it is Cn is equal to 1 by En integral t1 to t2 f of t x n of t dt. You can cross multiply these two equations. Cn En is equal to integral t1 to t2 f of t x n of t dt. So I replaced integral t1 to t2 f of t x n of t dt as Cn En. Cn En. Okay. And in the third term also I modified here. Sum of n is equal to 1 to n Cn square integral t1 to t2 xn square of t dt. What is that xn square of t dt? Nothing but En only. You see here. That is also shown in this slide as the top. We know that integral t1 to t2 xi square of t dt is ei. That I change as n as a variable. Xn square of t dt is en suffix. Okay. So in the second term, the integral function I substituted as Cn and En. And third term, the integral term as substituted as En. Okay. Now, simplify this expression. The sum of that is equal to error energy is equal to integral t1 to t2 f square of t dt minus 2 into sum of n is equal to 1 to n. Cn into Cn is a Cn square En plus sum of n is equal to 1 to n Cn square En. So the second term and third term, you see, both are the same. But here the minus 2 and this one is a plus 1. So minus 2 plus 1 is becomes of minus. Okay. So integral t1 to t2 f square of t dt minus, I am taking that only the function. You take this common, sum of n is equal to 1 to Cn square En minus 2 plus 1. What is a minus 2 plus 1? Minus only. So minus sum of n is equal to 1 to n Cn square En. We'll get the two functions. E is equal to E suffix E is equal to integral t1 to t2 f square of t dt minus sum of n is equal to 1 to n Cn square En. Okay. So now I use this expression. What I wrote in the yesterday's class, the mean square error, the formula is E square of t whole bar is equal to E square of t whole bar is equal to E suffix E whole divided by t2 minus t1. Okay, t2 minus t1. The difference between of the upper time equation and the lower t2 minus t1 is equal to, what is the E we got? E as integral t1 to t2 integral t1 to t2 whole multiplied with it f square of t dt minus sum of n is equal to 1 to n Cn square En. Cn square En. Now what is the equation we got after the deriving the mean square error is E square of t whole bar is equal to 1 by t2 minus t1 whole multiplied with integral t1 to t2 f square of t dt minus sum of n is equal to 1 to n Cn square En. Okay, now the last sentence you can see the sum of n is equal to 1 to n Cn square En is always a positive value only. Always positive. So if En is tends to 0, then only the n tends to infinite. Error energy signal. E is tends to 0 if E suffix E tends to 0 as n tends to infinite. So E, in that E we have there is a summation is there. In that summation the capital N, if that capital N is extended to the infinite, why I am extending to the infinite, we are getting that it is a positive value only. From 0 to n is also positive values. Up to I am extending 0 to infinite. When error mean square error and the error energy are related as the function. The sum of n is equal to 1 to n, Cn square En is always a positive. So if E tends to 0 as n tends to infinite. Okay. And now the mean square error approaches to the zero value when n tends to infinite. You see here, the with e square of t whole bar is equal to 0 means the numerator term. As a numerator term is a 0 as n is tends to infinite. So it becomes of the 0, 1 by t2 minus t1, the integral t1 to t2 f square of t dt minus sum of n is equal to 1 to n Cn square En. So when it becomes of the 0, when n tends to infinite, error energy tends to the 0 value. When equating these two functions, integral t1 to t2 f square of t dt is equal to sum of n is equal to infinite Cn square En. From f of t, the sum of n is equal to 1 to n Cn xn of t. Okay. So I'm taking the f of t as from the orthogonality in approximation signal. Approximately the f of t is equal to sum of n is equal to 1 to n Cn into xn of t. We know. So that f of t is changes as n value from n to the infinite, n1, n is equal to 1 to infinite Cn xn of t is nothing but a generalized Fourier series. The equation what we got from this here, from the mean square error and approximation of orthogonal function, we got the error energy signal is becomes a 0 when n approaches to the infinite. N, capital N approaches to the infinite, my dear students. In that, the f of t is equal to the sum of n is equal to infinite Cn xn of t. This is an equation, we can call it as a generalized Fourier series equation. Okay, a generalized Fourier series equation. You can remember this one. In further units, the Fourier series, Fourier transformation, Laplace transformation, and the Z transformation will get that Fourier series. We derive this from this equation only. A trigonometric Fourier series, exponential Fourier series, and polar Fourier series is there. That exponential Fourier series and the polar Fourier series will derive from this generalized Fourier series only. Okay, f of t is equal to sum of n is equal to 1 to n Cn xn of t. Following. And this totally we can call it as it is said to be a complete or a closed set if there exists no functions, number of functions from which the integral t1 to t2 f of t xn of t dt is equal to 0 for n is equal to 1, 2 and so on. A complete set of orthogonal function. When we say if any set is given in the range of the signals, if any set is given in the range of the signals, that set total set is complete set of orthogonal when we can say means by taking this equation integral t1 to t2 f of t xn of t dt is equal to 0 for n is equal to 1 to 1, 2 and so on, the capital N. Okay, what is the equation for the complete set of orthogonal function? The Ci is equal to integral t1 to t2 f of t x I of t dt whole divided by the integral t1 to t2 xi square of t dt. That integral x t1 to t2 xi square of t dt is nothing but energy signal. That energy signal is a EI only. Understood, my dear students? Is we can call it as a closed or a complete set of orthogonal function. When we say when n is tends to or n approaches to the infinite value. Understood, my dear students? So with this, we learn all the topics of the orthogonality. Orthogonality in vector, orthogonality in signal, orthogonality in complex functions, orthogonality signal space, and orthogonality of approximation signal, and also mean square error. Whatever we derive the expression for the approximation signal, we can call it as a complete set of orthogonal functions. Ci or the Cn is equal to integral t1 to t2 f of t xi of t dt integral t1 to t2 xi square of t dt, where I is 1, 2, and so on, the capital N. That capital N tends to infinite, then only we can say it is a complete set of orthogonal function or the generalized Fourier series equation also. Understood? In the tomorrow's class, we can take the examples, a complete set of orthogonal, and these examples is a very important, my dear students. A complete set given it is a 1 cos omega naught t, cos 2 omega naught t, and cos n omega naught t, and sine omega naught t, and sine 2 omega naught t, and sine n omega naught t are orthogonal over interval of t naught is equal to 2 pi by omega naught is given. Okay, the most of in the previous papers, the 10 papers we can set, in the 8 papers we have this question. Okay, so it is a very, very important, the complete set of orthogonal examples, cosine function and the sine function. How the cosine functions are becomes a 0 and how the cosine functions are the zeros, and how cosine and the sine functions is a 0, then only the given set or the complete set is orthogonal. Okay, the tomorrow's class we can continue. Now let us see, some of the students are so 453. Uma, please tell me what you want. Any doubt is there? 453, Uma. Please. She is there. Anyone? Some of the students are raised hands. Any doubts is there? Please ask me. I will clarify your doubts. And 453. So Uma, chatting that it is a Govinda, Govinda. Very good. I remember you, my dear students. 453 Uma and 443. Sir, left side image is not clear. Okay, I will see in the tomorrow's class that one. Still anything? Any doubts is there, my dear students? You can raise your hand. I will clarify your doubts, but don't chit chat such a nonsense in the chatting box. 453. If you do like this, don't come into my class. Please quiet and don't attend to my class if doing like this means. Very good. Everyone is logged in with your hall ticket number and name, and still one Yashwant. Ashwant. What is your number? And one student, the 461, is writing the name as a special characters. So I'm not allowing that person. 461. Yesterday also is same thing. He's not writing his name. Is there Ashwant? Either he is a triple student or it is a EC. Is there Ashwant? Very good. Some of students are simply owning that, not listening anything. That is up to you, my dear students. Okay. Any doubts? Please rise. Today's class or the previous two classes also. I will explain any doubts in the signals and different types of the signals and system and orthogonality concepts, vectors, signals, approximation signals, signal space, complex function, and complete set of orthogonal also. Another one, today we discussed about the mean square error. Is there any doubt is there in the derivation part or in the equations, simplifying the equations also? I will explain now itself.
Hello, sir.
Tell me the 4636 Gopi. Tell me, what is your doubt?
Relation
Very
between
good.
mean square
Pardon?
error and energy relation అర్థం కాలేదు సార్.
Once again, you can tell me. Mean square error equation and
ఎనర్జీ రిలేషన్ చెప్పారు కదా సార్. రిలేషన్ బిట్వీన్ మీన్ స్క్వేర్ ఎర్రర్ అండ్ ఎనర్జీ.
okay. Okay. I will explain. Okay, very good. See, this is the equation. So mean square error and energy signal equation. See, the energy signal, error energy signal is in the denominator. See, the E square of T whole bar is equal to E suffix E, T2 minus T1 is a formula for the mean square error and energy signal equation. So we got the error energy signal E is equal to see what is the E is equal to after substituting of integral T1 to T2 f of t xn of t dt as Cn x En, and here also the integral T1 to T2 xn square of t dt as En. After simplifying this equation, the error energy signal E suffix E is equal to, okay, we got the two terms, integral T1 to T2 f square of t dt minus sum of n is equal to 1 to n Cn square En. I substituted these two terms in the mean square error. The mean square error and error energy is related as, so 1 by T2 minus T1. In the numerator we have the integral T1 to T2 f square of t dt minus sum of n is equal to 1 to n Cn square En. This is the relation between of error energy signal and mean square error. Got it, Gopi?
Okay.
Still any doubt is there?
No, sir.
No. Very good. Thank you. Still anyone? Any other one?
Hello, sir.
Who is this 470? Tell me.
Sir, if any possible way to send the PDF to our CR, sir, today class material.
You can download this one. These are only the class notes directly. You can take the screenshots. These are notes only directly. My notes only this one. Take the screenshots.
Okay, sir.
Every time if any class is going on, you can take the screenshots.
Okay,
Then you can,
okay.
that is only the notes only.
Okay, sir.
All right.
Okay.
Still any doubts, my dear students? I appreciated Mr. Gopi and Abdul 470. He raised both are raised the doubts. Still anyone is there? And another one, Uma. I need Uma. Why she wrote Govinda. What is the doubt? I don't understood what she wrote in the chat box. She is there? Okay, students. Thank you. Thank you, one and all.
Thank you, sir.